Hey, what's up, guys? This is Chung here again. So this time, LeetCode number 1938, maximum genetic difference query. So this one is a pretty difficult one. Like, to be honest, it has a few small sub problems we need to solve first. Okay, so you're given like a rooted tree, right, consisting of n nodes number from 0 to n minus 1, and each node's number, right, denotes to its unique genetic value. Basically, the node number is its value. And the genetic difference between two genetic values is defined as a bitwise OR, right? So this is a pretty common type of problem, bitwise OR, okay? And then you're given like an integer array parent because we're gonna need we can use this one to build like a tree, right? And then you're also given like array queries, right? Where the queries has two values. The first one is a node, right? And the second one is a value. So for each queries, we need to find the maximum genetic difference between the value of and all its parents of the current node, including this node itself, right? And then we want to return this answer, right? For each query. So basically, what does it mean? It means that, first you're given like a tree, right? And then in the form of a parent, and then you're given like a query. So for each query, what we need to get is that, the first one is a node, right? So this one means that, from the current node all the way back to its parent, right? Then we have like different values along the way, right? And we want to get the maximum bitwise OR, right, between this value in the queries and all the values uh, on this path, right, to the root. That's why, so this is the tree we have here, right? And then the queries we have is 0, 2, 3, 2, and 2, 5. So the answer is 2, 3, 5 because for root 0, right, I mean, there's nothing, right? For root 0, it's there's only one node, right? We can use, which is 2. Basically, 0 x bitwise XOR, right, to 2 equals to 2. Right, that's why we have 2. But for 3, right, for 3, we have 3 nodes that we can use, which is 3, 1, and 0. Right, among those 3 nodes, the biggest value we can get is this one, is because it's 1 with a difference of, that's going to be the 2x or 1. Basically, the value is 2 here, right? And then the best we can use is this node, which is 1 equals to 1, which is 3, sorry, equals to 3. And the third one is 2 and 5, right? So for 2 and 5, we have 2, 1, and 0. We have 3 nodes to use, right? And among those 3 ones, I believe we pick 2 because 5x or 2 equals to 7, which will give us the biggest one, right? So that's basically the description of this problem, right? And then we have some common like constraints, right? I think those are pretty common ones, and the value is also this one, right? Okay, so for this one, and every time when you get say a bitwise XOR plus a bunch of queries we need to solve, I think the first thing we should always think about, consider the bit trie or the bit prefix tree, because the bit prefix tree can give us like a very I think all of constant time to query the values, the biggest value among all the available numbers. In this case is all the parent nodes, including the node itself, right? And for those who doesn't know what the bit prefix tree is, that maybe I can give you a brief introduction here. For example, we have, like I said, we have a bunch of numbers along the way we want to compare, right? Among those numbers, we want to quickly find which number can give us the best or the biggest XOR value with the current value, right? So where should I start? So first we need to convert each of the numbers to its bit value. So let's say we have these two values here, 1, 0, a few numbers here. Okay, and then we have 0, 1, 1, 1, 0, and then we have another one, 1, 0, 0, 1, 0, right? There could be more, right? So those are the available numbers, okay? And our current number is what? Our current number is this one. Let's say the current number is 0, 0, 1, 0, 1. So this is the current number we're trying to use, and we want to find the biggest number, right? That can get, which can give us the maximum value here, right? And how should we do it? I mean, obviously we want to check the values bit by bit, assuming we only have like 5 bits, 5 bits in our case, right? So the ideal case is what? Ideal case is like this. Ideal case, if we have a number with this 1, 1, 0, 1, 0, right? This is the ideal case, because this will give us what? This will give us 1, 1, 1, 1, 1, right? Which is the maximum possible number we can get, right? But obviously this one, as you guys can see, this one does not exist in this set, right? But you guys see the pattern here. So basically, we want to get as many ones as possible, right? And okay, so which means that we want to get as many ones as possible, and we want to get the ones can give us the biggest value first, because right. So which bit can give us the biggest value? We obviously is the one from the left side. This is the first one we want to get, right? That's why what we want to check is that we want to see, okay, if there's any number that has this bit equals to 1, right? If it is, then we know, okay, at least we can get what? We can get 2 to the power of 4, right? Which is 16, right? So basically, if we have a number who has the value bit value equals to 1 for this one, I know at least I can get 16, right? And the reason we want to use this one first is because if there's one has a bit value equals to 1 here, we will definitely use that number, because otherwise, if this one is 0, even though everything else is equal to 1, right? So what's this value? This is 15, right? 15 is still smaller than 16. That's why I want to greedily pick the ones from the left, right? So now we see, okay, so we have 1, right? So there's 1 here. There's one. Actually there are two numbers that have 1 for this bit. Okay, how about the second one? Second, we're also trying to see if there's a 1 here, but since we already pick this one here, after the 1, both of them have value 0, right? So which means what? So which means the second one is not possible, because even though we have 1 here, but this one coming from the 0, right? Which we didn't use, because we picked the ones with the 1. We picked those two numbers with the ones here. That's why we have to use 0 here, right? So which means 0 is not possible. How about the third one? The third one, what we're looking for is a 0. Do we have 0? Yes, we have 0 here, right? That's why we have what? Then since we have this one, we can have like 2 to the power of 2, right? If we keep going, right? So the next one is what? The next one we're looking for is 1, right? Do we have 1 here, right? We have 1 here, which is this one, because since we have already followed this path, now this one is not available anymore. We have to go with this one, right? That's why we have another of 1. How about 0? Yes, we have 0. That is it's 1, right? So that's basically the values we can get, right? And this is how we use the binary fixed tree, because the way binary uh, sorry, not binary, or bit prefix tree is like this. So we have a root here. So for root, right? So each root can only have possible either 0 or 1 node. Either either one node or either has node 0 or node has 1. So for this one, we have 1 here, right? So that's why, we have 1 here, okay? And then we have 0. So let's define the left one is always 0, the right one is always 1. Then we have 0 here, okay? And then next one is 1, right? So we have 1 here. And then next one is also 1, okay? And then the last one is 0, okay? So that's how we insert the first number into this bit try, right? And then the second one is 0, 1, 1. So we have 0, and then we have 1, right? And the next one is also 1, also 1. Last one is 0, right? The last one is this one, 1, 0, 0, 0, 1. So we have 1, we have 0, and then we have 0 in this case, right? And then we have 1, and then we have 0. Right? So that's how we build this bit prefix tree. And when it comes down to how can we use it, right? Like I said, we start from this root, right? And we check, we're looking for the 1, right? For the first one. Okay, so that's why we'll go here, right? Because we have 1. And then from the 1 here, right? We're also so the next one we're also looking for 1, right? But we don't have a 1 after this one. We only have 0, right? That's why, we'll move to 0. And notice that we only accumulate the answers when we can find a match, right? Because otherwise, this bit will be 0. 0 means there's no value, right? To be added. So that's why we have 0, right? Because we don't have anything, right? So we have 0. And then the next one is what? Next one is also we're looking for 0 in this case, right? That's why we'll go here, right? So that's why we're coming here. And then the next one is 1, right? And then the next one is 1, and then the last one is 0. That's how we traverse this one down the row, right? To get the maximum possible XOR we can get, right? Okay, so that's the basic idea of the prefix tree. I hope you guys understand how it works. Okay, so given this one, right, the next problem is that how can we find this kind of basically candidates, right? We can do the XOR. So let's go back to the problem, right? As you guys can see, right, the query is for the node, right? And so the brute force way is that for the current node, we want to find all the parent nodes, and then we add all the parent nodes into the into into the bit try, right? And then we just do a query on that. But if we do it that way, for each of the query here, right, to find all the parent nodes, worst case scenarios we need n time, right? And then for the queries here, it's going to be n times n, right? Going to be n squared time complexity for that. That's why we cannot use that because with this constraints here, I think it will most likely TLE, right? That's why we have to find like a more efficient way to do the query, right? So what we can do is that since we have a tree structure here, right? I mean, we can do the query along the way while we're doing the DFS traverse of the tree here. So what does it mean? It means that we have everyone knows DFS, right? So we have DFS here. So DFS we have a U here, right? Every time when we visit a U here, right? We're gonna insert this one into the bit try, the prefix tree. And after DFS finish, we're gonna remove it. We're gonna remove the U from the prefix tree because for example, for this one, right? So when we have 0, 1, and 2, right? So once two is finished processing, and then the next one from 1 is going to be 3, right? But at this moment, let's say 2 has already been added, right, to the prefix tree. Now, when we're processing 3 here, we don't want the 2 to be we need to remove 2 from the prefix tree, because obviously for 3 we only have 3, 1, and 0. We don't have 2. That's why we have to find the efficient way to remove the 2 from the prefix tree, right? So how can we remove it? A trick is that we can keep a count. We can keep a count for each of the node in the prefix tree. And every time when we insert, we increase that the count by 1, and when we remove, we simply just do a decrease that. Okay, and then later on when we try to query the prefix tree, we also need to check if the count is greater than 0, right? If it's 0, then we know there's a value there. This bit has a value, right, from some numbers. Okay, and that's that, right? Now, as you guys can see, so for this one, we can simply just piggyback on this DFS traverse, right? And then to calculate the queries, right? Basically, what I mean, what what I mean is that every time when we have like a U here, after inserting here, we can do something here. So what we can do, because at this moment, right, everything for this U, for this number U here, for this node U here, has already been inserted. All the parents has been inserted into the prefix tree. That's why from here we can do the query. We can query for this U, right? And we can query for this U for all the queries that has this number, has the node equal to this U, right? So let's say, for example, we have 3 here. Let's say we have 3, 2, and there's another query 3, 5. There's another one of 3, 6, right? So at this moment, right, I can answer the query for all 3 queries because of this 3 here. Let's say U is equal to 3 at this moment, right? Because at this moment, like I said, everything, all the parents of 3 has already been added to the prefix tree. Okay, and right, and after that, we also need to remove it for the U, because here, after answer the queries, we're gonna also do a DFS, right, of V here. V is the children of U. Okay, I think that's the basic idea here, right? So, and yeah, I guess then we can start coding. I think the implementation is a little bit long here, but I will try to make it short. So first, for me, I always prefer to create a node for the prefix tree. Self, okay, self dot children, okay, have children equals to this, and have self dot count, right? Like I said, we need a count, and oh, and I think another thing I forgot to mention is that for the bit prefix tree, how many digits we want to check, right? That's the number of digits we want to check depending on the biggest number for this problem, right? Because for example, previously we only have like five digits, right? Because I'm just using this one as an example, but for this one, as you guys can see, we have 2 times 10 to the power of 5, right? So which means that we need probably we need 10 to the power of 18 to cover everything, right? Because this one, so I think this one is 3 something. I don't remember the exact numbers, but I think 2 to the power of 18 can cover this big range here, right? Because obviously we want to have like enough bits value to cover all the values here, right? And cool. So so where shall we start? Okay, so first one is the root, right? Let's try to implement the prefix tree here. So for this one, since we need to do both the insert and the remove, so I'm going to use this one as an update. So we're gonna have a number, and we have a value here, right? So basically, this number will be, when it's insert, this value will be 1, right? And when it's remove, this value will be a -1. Okay, current equals to root, right? So for I in range of 17 minus 1 minus 1, right? Because like I said, since we're trying to when we're trying to query the prefix tree, we're trying to query it from the leftmost bit value, right? Which is this one, right? That's why when we do the insert, we want to do it in the reverse way, right? We want to insert this one into the prefix tree first. That's when, because only then we can just after the root, the next child will be the leftmost digits, right? That's why we do it in the reverse way. Okay, and like I said, since 2 to the power of 18 is enough, that's why we use 17, because 17 to 0 is 18, right? So the bit value is like this. So this is gonna a little bit bit manipulation here, right? We do this one, and do we n of 1. That's how we get the leftmost, not the leftmost, this number of this bit value of at this index, at this position, right? And then it's like the standard prefix tree implementation, right? Template. If this one not in the current dot children, right? We create this child node, right? Equals the node of itself, right? And then we current equals to current dot children dot bit, right? And then in the end, don't forget to increase the count by this value, right? Because yeah. And then the next one is a query, right? Query of number. So this one similarly as this one. Oops. I can this one I can copy and paste. The structure is the same, but this one is different. So now okay, so we also need the answer here, right? The answer is going to be 0 here, and so this time we need a target, right? Remember, the target will be the reverse value of the original value, right? Which is that's why I do a XOR in the end. That's how we get the target. And for this one, we do so if the target is in, now this time the target is in this one, and remember, since we have a count here, and the current dot children dot target dot count is greater than 0, right? That's when we will increase the answer, right? By this value, okay? And then answer equals to answer dot children dot target, right? Else, right? Else if it's not there, right? We will not do the answer, will not increase the answer, but here we'll basically do the XOR, this one, right? Because at this moment, if this one does not exist, obviously the other side must exist, right? Because we have already populated that. Because if since there's always like a path to the end, right? So if this one does not exist, then the other side has to exist, right? Because there has to be a path follow to the end, to the leaf, right? If this one's not there, the other side must exist. That's why we can safely assign the current with the target XOR 1. Okay, and again, so this part, if there's no count here, right? So this one is enough. But since we have this counter here, so which means that even though this path exists, but if this node, even though this node might exist, but the count could be 0, because it could be we add it, but now then later on we remove it. That's why we have to check both of the two things here. Okay, and yeah, so that's it, right? And I mean, simply in the end we return the answer. Oh, sorry, this one. Yeah, so this part is not needed, right? So that's how we query the bit prefix tree. Okay, cool. So that's the prefix tree, and the rest is what? So let's try to build the graph. Okay. Well, actually it's tree, it's not a graph, right? tree is like this. So we're gonna have default of the list, right? And then we also need to find the root value. Okay, so that's why I need to define the root value. It's gonna be a -1. Okay, and then for I dot parent, right, in enumerate of parent. Okay. If the parent is equal to -1, then we know, okay, so the current this index is the root, gonna be what? They're gonna be I, because later on when we do the DFS, we need to start from the root. That's why I use this one, right? And since we already have a root here, I need to use a different variable name. And then the tree dot parent, right? Dot append I, right? So that's how we build a tree. And then the next one is what? The DFS, right? So let's do the DFS here. Because later on, we're going to do a DFS. It's going to be DFS of the root value, right? And then we return the answer. Oh, we haven't defined the answer yet. The answer is, okay, it's here. So we have the answer is going to be the 0 of length of queries, okay? Yeah, so that's the answer, right? And then return the answer later on, right? Okay, now the DFS. So we have a U here, right? U and V here. So first, every time we enter a node here, we're gonna update, right? We're gonna insert, basically we're gonna update the U with 1, right? And later on, we're gonna remove it, right? U -1, right? That's how we, and then let's finish the DFS first. So we have and then for V in tree of U, right? We do a DFS of V, right? So this is the DFS template, right? Pretty straightforward. And like I said, on top of this one, right? Before doing this, now we can answer queries, all queries, basically all queries for you, right? And okay, yeah, in order to do that, I think we also need to create like a dictionary between the node to the queries, right? Because if this node here could have multiple queries that we can answer, right? That's why let's see. Okay, let me create another dictionary. I'll just call it a node to query. It's gonna be another dictionary, right? So for this one, index, and we have U and value, right? In enumerate of queries, queries. So the key for this one, obviously is the value itself, right? And then we need to append two things. The first one is the index. Second one is the value, right? Because we need the original index to update the answer, right? Okay. And so let's go back here. Now we can answer the queries. So for index and the values in node to queries of U, right? So the answer of this index equals to the query of the value, right? And yep, I think that's it, right? Okay, let's try to run the code. Finger crossed. Okay, accepted. Nice. Let's try run it again. Okay, cool. So this one passed, but as you guys can see, this one is it's almost TLE. You know, um, I don't know. I think that's how this problem, the test case was given, and this maybe it's because it's gonna be harder for Python. You know, I believe if you use C++ or Java, you may get a faster runtime, but for Python, this is just as I mean the best I can do, I guess. So almost TLE. Um, So let's take a look at the time complexity, right? So here, right, so the update and queries, so this one is like what? 18, right? As you guys can see, right? So this one, you can think of as an O of 1, but it's anyway, it's an O of 18. And so for the DFS, right? So for the DFS and for this kind of queries here, so how many queries we have? We have this queries here. So the queries is this one, and the so the node is, let's say, is n, right? And this one is m. Okay. So because we have this many queries we need to answer, that's why we have this for loop here. But anyway, but all in all, in total, so what we have m plus n, right? We have m plus n thing we need to answer, and on top of this one, we have 18, right? Times that. Because in total, the DFS, right? The DFS in total will traverse n nodes, right? And among all those kind of n traversing, will answer m queries for those for this many nodes. That's why total we have m times n, and for each of them we're gonna do either query or update, and either query or update, the time complexity is O of 18. That's why this is the total time complexity, right? Yeah, I think that's it, right? I know this one is a long one. I don't know. Just to recap, right? So first thing is that every time we see this bitwise OR and a bunch of queries, always try to use the prefix tree, right? At the bit prefix tree, and then we try to build a bit prefix tree uh, with a count, right? So because we for each queries we want to only we need to make sure the prefix tree only includes the parent node for the current node. That's why we also need a count to also help us to identify, right, if this node has a value, has a number associated with it or not. Okay, that's why we have update, right? We either increase or decrease. Okay, and once we figure out the prefix tree, the next thing is that we need to use the DFS, right, to efficiently traverse all the nodes while also while traversing the tree. We also want to answer the questions, the queries for the current node. That's why we have this structure, right? So first we have DFS, and every time we enter a node, so we insert into the prefix tree, and then later on we remove it, and then in between, right, we can answer the questions for all the queries for this node. Okay, and the rest is just a bunch of I have to answer here, return here. The rest is just a bunch of like miscellaneous stuff, right, to help us to accomplish our goal, right? Yeah, I think that's it for this one, and thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.